we are beginning a unit that's going to be looking at two specific different conserved quantities. And one specific one that we're going to start talking about initially is energy. So energy is just stuff, and well, we'll try to come to a conclusion before the end of the year. What exactly is this energy stuff? But one thing we know is energy is a conserved quantity, and there's a law associated with it called the law of conservation of energy. So that if this guy, who probably has some energy, puts it into this system and takes this box in, raises that box so that he pulls the rope downward in some fashion, the box will then go up to some height. And when he does that, what he is doing is this guy is doing work. Now, maybe this guy has got some kind of he's a bit of got some shenanigans in mind, and he's waiting for some unsuspecting, who knows, individual to walk below, so that he can let go of the rope, and this box will suddenly become, will release the energy that was given to it by this dude doing work. So, as a virtue of its position, it had some type of stored energy, which we will call gravitational potential energy. So, this guy does work. He loses some energy, but the energy that he did in work goes into the box as gravitational potential energy. When he releases it, gravity then does work on the box and converts the stored potential energy into the kinetic energy, which is then kinetic energy, which is the energy specifically of motion. So what we're going to be looking at in this unit is, in one case, energy as a conserved quantity. So let's go and examine some of that right now. Alright, here we're going to go ahead and talk about work specifically. Now, if you do work on something, you are changing the amount of energy it has. It represents a change in energy of some object. And the thing that does the work, frankly, too. But this is somewhat circular reasoning, because you may remember from some other class that energy is defined as the ability to do work. And if work changes energy, you've got this circular reasoning thing. Well, let's specifically look at what like work in terms of a formula. If you do work on something, it is defined as applying a force on an object over some distance, where the force we apply is parallel to the displacement of the object. So if you have this lady in her, look like maybe they're jorts or something, if she walks forward while applying a force up at this angle, that force is not directly causing the work. Well, it is causing the work. However, we have to understand it is only the x component of that force that is doing the work. And so the interesting thing is if this force, what was that noise? If this force, it represents a net force being applied over some distance. Now, it doesn't have to be a net force, we'll discover. If there's a bunch of friction, some of the energy that is given to the bag is quickly transferred into thermal energy through friction. But if it's frictionless and a net force is being applied over a distance, then this work makes something very specific happen. And we can actually break this formula down to find out what specific thing happens. Well, let's take a look. And let's change up the color a little bit here. We know that net forces are equal to mass times acceleration. So I can throw that in with my D and say that work when done by a net force is equal to mass times acceleration times distance, or MAD. That's mad and crazy. Mostly mad. Okay, I'll stop being ridiculous. Moving forward, this is interesting. This AD, this distance, for some reason we decided to start using D instead of the letter we'd been using the rest of the year, which is really X for displacement. So this is kind of like saying, instead of MAD, rather, Max. Isn't that a movie? At any rate, I look at this ax, and it really reminds me of something. It reminds me of 2ax, which I remember from a kinematics formula. What are you doing, Heckman? Well, I'm trying to break this down into what actually happens when you apply a force over a distance. Well, if I apply a force over a distance, I see an ax in there, and I know that the MAD is the max. They're the same thing. Same. That something happens, and since I have a formula with an ax in it, it seems like I could rearrange it and multiply the kit and caboodle by mass, and I would have the max, which is the MAD, which is work, which is force times distance. Okay, well, let's do it. Well, quick and dirty algebra shuffle. New color. Well, I know that if I rearrange this thing algebraically, I get this. VF squared minus V naught squared. Now I want to get rid of that 2 because I'm trying to get ax by itself. So I'm going to multiply through by 1/2. 1/2. Seems reasonable. And that would be equal to ax. Now, if I step in and multiply that by mass, everything by mass, multiply by mass, I get, and distribute, what the heck, why not distribute? We get 1/2 mvf squared minus 1/2 v naught, m, I forgot the m, mv naught squared is equal to max, which, don't forget, was actually equal to MAD, which was actually equal to force times distance, which is all an expression for work. And whenever you have a minus here, this is like saying a difference or some kind of change in. Now, didn't I just say that this is equal to change in energy? So apparently this stuff over here, this formula, is some kind of energy, and specifically it is kinetic energy. Kinetic energy can be calculated by taking an object's 1/2 an object's mass times its velocity squared. Remember, kids, hugs not drugs. Go ahead and click on Go to Potential Energy to see the next video.